Welcome to the next presentation that has the name NixOS, Poorly Functional Package Management. Our presenter is Vladim. We can start.
Okay, thank you for introducing me. So I'm going to talk about package management and a distribution called built on top of it. And well, I'm sure you have seen thousands of distributions. Linux is famous for this. I will try to convince you that this view of package management is quite different, and it gives us something more than we usually get. An example motivation from my life, or actually my sister's. So she was upgrading Ubuntu, and there was kind of a hardware problem. It was interrupted, and the result was that the system booted, but the X server wouldn't start. And that was a bad problem, because she doesn't know what command line is, and well, she was completely unable to fix it or do anything about it. That's I'm not very sure how other distributions solve this, but certainly for Ubuntu this doesn't work very well. So it can happen. And okay, so that's one thing we would like to have: atomic switching of versions. That's certainly useful, but there are many other useful properties that also later. So how can we achieve atomic switching? Well, certainly, if we think about it, at the switching moment, we need to have both the versions in a valid state. So we need to have them at once. But if some configuration changes, like libraries or something, they can't be on the same path. So if we want to use a complete, a common file system, common namespace for the files, and not some virtual thing that is different for different processes, then we certainly can't have packages on standard paths, especially libraries. We can't have that. And that's quite a diversion from traditional distributions, because, well, it's not very common to have different than the standard paths. But we can't avoid it if we want to really ensure some properties. So what Nix does, and that's not so special, many other distributions does this, that we have separate directory per every package build. So every instance of a package is on a different place, and it never changes. So the thing is that when we change some dependencies, we could potentially break the package. We don't really know whoever depends on us. So we need to use absolute paths for that. So the packages don't get changed inadvertently. Well, anyway. Okay, so that's one thing. And another is, well, when we have any two versions at the same time when we switch on an upgrade, well, it's quite natural. It doesn't cost us more to be able to have any number of different configurations at once on the system. and being able to switch among them. And when there are so many things, it's not very clear how to create the names, the paths. Okay, so here we use hashing, where the hash encodes all the configuration of the build, concrete build of some package. For example, here there is some common prefix to the store for packages, the hash, which is quite long, and then the standard things like name with version and the tree of the package. The hashing has the advantage that whenever we have the exactly same configuration, it gives us the same hash and so the same path, and we can reuse the build. Okay, so that was a basic idea how it is done, but now I should tell something more about what is an X package, or how we model it, how we view it. For these packages and configurations, we use a simple, purely functional language. Well, I should say, what do I mean by the purely functional? In case you don't know it, it's connected to the things I've already a bit mentioned, that we have a referential transparency. That is, whenever we allocate some memory, we define its contents and we never change it anymore. Yes, so because some others may have pointers to it and they don't expect to change it, it could break them. So the only way this gets deleted is when everyone loses connections to it, and it can be garbage collected. And that's an essential property. And so package in this language is just a simple function. Okay, function, and it takes some parameters, of course, and these are the build time dependencies, options, and other such things. And the most important thing here is the purity. Okay, so that's the fact that the only way we can change the output of a function is by changing parameters, or, well, obviously changing the function, or also changes or can change the output. So these are functions in mathematical way. So there are no side effects and similar things. So one important advantage of this is that we get a deterministic build recipe. So when we supply all the parameters, that's the libraries, configuration, etc., we should get a recipe that completely describes how exactly the build occurs, and it determines the output uniquely. Okay, well, an example of what does it look like. I hope it can be seen a bit. So here's an example how there in the Linux language a package could look like. It's well, quite similar to some other things, like if you saw these Gentoo builds or the open build service of SUSE. So that there are some parameters as the standard build environment, something that fetches us the sources, and we just simple description. There, well, the simple description, so some kind of name chosen, we fetch the source, check its hash, we supply the build inputs, which results into setting some environment variables, like include paths, library paths, and so on. We could do much more, supply patches, configure flags, and some other actions, quite almost anything. And also some metadata. Okay, so that's a package. It's pure function. And well, why do we even bother with these properties? What do we get from them? That's very important, because that's why we do it. The purity of builds gives us the fact that all the builds are reproducible, deterministic, and independent. That is, we take the recipe and send it to some machine far away. That's for computations, for building, and it sends us the output. We can be quite sure that the output is the same as we build it on our machines or anywhere else. It's always the same. And it doesn't matter on the state of our system, if we have some additional packages installed or whatever. It's always the same. We also get implicit sharing via the hashes. If the things are the same, the paths are the same, we can share it, and safely. Because, well, to forge the cryptographic hashes is, well, very hard, or it is not known to be possible, so that's also a good thing. And one important thing is the trackability of dependencies. All the dependencies are declared. The builder doesn't see anything else than its build inputs, the parameters. If there are some other packages, it does not see that. And that's important. Then we know what we depend on. That also, I've seen this to be a problem that, well, in case we fail to supply something, the builder fails. Often on many systems like, I don't know, Gentoo Portage or somewhere else, the build just succeeds because we occasionally, by luck, have the necessary package on the system. But we don't know it, that it is necessary. And that can be a problem, unspotted problem, and that's bad. Okay, so for example, this gives us advantage in easy deploying. So suppose I have some my tuned build of Firefox on my machine and I want to use it on my other machine somewhere else. Well, since we have the exact dependencies and everything encoded, we track it. It's as simple as this one command. Okay, so we just copy the closure, everything that is missing on the target machine, and it's there. And another important set of things is safety. With this independence of the packages and the switching, we can do atomic switching, and we can instantly roll back easily any changes, because the state is still there until we garbage collect it. We lose some pointers. We can have pointers to some older states just in case we found out that our update wasn't as successful as it seemed to be. And from this, we can allow any user to install anything, because it can't affect the other users. Yeah, if one installs into his environment something, it doesn't change the other users. And if it happens that they install exactly the same thing, well, due to the reusing, they reuse the same paths. So they are implicitly shared, and that's also good. And all this purity gives us also a transparent way of binary deployment. As I said, we can build everything on a farm, and we know that that is the same as if we build it ourselves. And we can do changes. The system knows it, that the farm doesn't have the way, and we build what we need in addition, but it's possible. And well, the binary patching, that's quite recent, a quite standard thing, so nothing special. At the moment, it was yesterday, I believe, we had something, almost 20,000 successful build of the, but these are only successful builds of the most recent versions of the trunk, the most recent version. There's much more, so it saves a lot of time, for example, compared to Gen 2 building, which is fantastic with its configurability. But if I don't want anything special, want the same as many other people, why not share the build time? Okay, so that was how we view package management. But when we have these nice properties, why not extend it to the whole operating system? Yeah, well, we can have stateless operating system where everything, all the configurations of daemons, etc., is generated from a set of configuration files, and the result, well, that's our build recipe, the configuration files from which we build the whole system by pure expressions in the same language. And that's really nice, because it's, again, deterministic, the result, and we can just send the recipe to another machine, redeploy it, or send binaries, and again we get binaries from the build farm. There's not much work needed. And the best thing is atomic switching. We have another version of the operating system. We just switch it, and there's nothing in between. There's not the crash from beginning. Yeah, so we have this even in the bootloader. So you can choose if the configuration doesn't work anymore. You choose any of the previous until you delete them, or they are garbage collected. Or you can even test them in a virtual machine. Just a simple command, rebuild in build VM. You get an image in the virtual machine. You can test your configuration before you switch to it, and roll back. Even you can switch it without rebooting, so as much as it is possible, because kernel can be exchanged at runtime, and also we usually don't want to restart X server and similar things. So, but much of services can be restarted. So this really nicely scales, and it's really practical, the principle. Okay, so what are the main points here of Nix? It was the purity and transactional behavior. So we have some build recipes that we edit, and it's not just a configuration, it's a complete language functional. But it's tweaked, especially that it is easy to write these recipes. Like there's nice URI syntax and similar. And we have transactional behavior, so we can the build is atomically made valid when it finishes, and when it fails, there's just some garbage temporary files, but nothing else. And it gives us easy combining of source and binary deployment through the build farm, and that really saves a lot of time. But still, we maintain the Gentoo-like customizability. All the packages are functions. Any parameters can be easily customized. You can create your own helper functions, because it's functional language. If you know, there's a lot of power in it. So you share as much as you can, and whatever you want differently, you build it, but nothing more. And that's quite good, or I find it good, but I won't say much more. So the current state is that Nix and NixOS is called experimental, but it's already highly usable. Many of us use it as the main systems on many computers, and for years now. And well, why doesn't it really matter that it is experimental and we can use it is the safety thing. Whenever something gets wrong, we can get back to any working state. And that's just wonderful. I have when I started really using Linux, I started with Gentoo, which was really wonderful for learning Linux, but there was much of time when the system was just unworkable, because I had only one processor, which wasn't too fast, and well, I often broke the system. It wasn't really easy to get back or forward or anywhere. So it is possible to run this distribution with thousands of build packages in about 10 significant contributors, which do it in their free time. So that seems quite good. And now we are gathering developing speed, the updating of packages and so on by moving the workflow to GitHub, which seems to have helped a lot, because it makes much easier to review the changes by others, and much easier for others to contribute the work they do just for themselves because they need it. But they are willing to share their work. So these are the main points. So, and I invite you to the resources on nixos.org, and eventually you can join us. Okay, any questions? The microphone, probably.
I would like to ask how do you handle multiple installation of single package? Like in Gentoo, you have, for example, Python packages that have installation in various versions, and currently, for example, it is not possible to have different configurations for them.
Yes, that's, I didn't stress it, but that's one of the important advantages. You can have any number of configurations of any package in any number of versions. It doesn't really matter. The hash gets different when you change the configuration of version, and it gets into another directory, and you pull into your environment anything you want just now. So you can have any number of versions. It doesn't interfere. Okay, here's probably some.
I guess on the same topic of having multiple versions of packages installed, I guess for rolling release distributions that maybe average users aren't running, but maybe a lot of people here might or whatnot, you're maybe getting a lot of packages of the same the same package, different versions installed at the same time, unless this feature is disabled by default. So I guess I'm kind of wondering, I don't know, with environments where people are running flash drives or solid state storage or embedded systems, like having this pile up in space usage, or for example, if like I have multiple versions of Apache installed because I'm getting like new versions with security fixes, which one is, I don't know, which one is running up at startup, or like how this would be handled. It seems like a fairly complex issue, actually, even though it's technically a nice feature to have.
I'm not really sure what was the main question. The blow up in space?
That's like one of the multiple things that might be an issue. Like, for example, in Nix OS, which I haven't run, is this feature enabled by default that when you upgrade your package, it keeps the older versions also installed?
You always keep the versions of before, because you don't know the other user can use it. He can have it in his environment, and you can't affect him. So you can run your garbage collector afterwards. So it might be deleted immediately, yeah, if you don't want to keep it. And there's, well, usually when, for example, when you upgrade libc, everything changes. Yes, but, well, the hashes change, but most of the files remain the same. And because they never get changed, they can be hard-linked or sim-linked, and they are in NixOS. So the blow-up in space isn't that large. And from the build farm, you get binary packages, so binary diffs. So it doesn't take much bandwidth anyway, so that's...
We have to finish this session now, sorry.
Okay.
We have the next presentation with Peter Senek. The theme is why proper logging is important even in the bootstrapping phase